Okay, welcome to section 2.1, day 1. We're still on day 1, and this is just the section, 2.1, day 1, this is the section about limits. And limits are defined using this notation, which you see here. The limit as x value goes to some number of a function equals L. L equals the y value. Okay, so the y value or the function value, and it's actually f at c, I'll put f at c, is the limit. Okay, so always keep in mind the limit is the y value or the function value when x goes toward that number. Now, some function or some limits are easy to do, you just substitute. Some you have to look graphically, some numerically, some you have to use some algebra to cancel out things. Sometimes we have to use some fancy trig work. So you'll see there's lots of different ways to get to limits. All right, please note that, you can check your answers graphically. Please note that if you need extra time to write down things, you can always stop these videos and then move on. All right, first of all, we're going to look at substitution, the easiest method. And the first thing you do when looking at a limit, plug in the number and see what happens. 3 times negative 2 minus 4. Well, shoot, that's negative 6 minus 4, that equals negative 10. That limit is equal to negative 10. It was easy to find. All right, the second one, if we plug in a 1, we have 3 times 1 squared plus 4 over 1. That's 7 over 1, or just 7. All right, that's substitution. If you plug it in and it works okay, you're good to go. What if substitution doesn't work? And you'll notice in this first one, if I plug in a 0, I'm going to have a 0 in the denominator. Can't do that. Big time fail. Okay, so whenever you get a 0 in the denominator, the first thing you try to do is factoring and canceling. Use some algebra to try to get that 0 out of the denominator. So if we look at the top of this function, we can actually, we'll keep the limit as x goes to 0, so remember what we're doing. We're going to factor out on the top. Sorry, you guys will learn that I have a crazy board. You're going to have to factor out an x, and here you have 2x minus 4. All right, so if you factor out that x and you have an x on the bottom, they cancel out, and you're left with the limit. Notice in the middle of my board, I have a little squiggly. You will see that often. Actually, I don't need a fraction anymore. I have 2x minus 4 over 1. Okay, now if I plug in a 0, we get a negative 4. So with just a little bit of simple factoring, that made that one able to work. Now, I think you did some of this with your pre-calculus teacher, who would be Miss Gallardo. So, this time we're going to factor the top and hope that we get an x minus 1 up here. Okay, because we have an x minus 1 on the bottom. If we have an x minus 1 and we put it with an x plus 2, that should be the factorization of this top. So we can cancel out these and then check out what our limit would be as x goes to 1 of just x plus 2. Well, that would be equal to 3 if I plug a 1 in for x. Okay, last but not least, let's do a little fancy algebra on this last problem. I'm going to even factor out, because if I put a 2 in here, I get a 0 in the bottom. So I immediately look to see, can I do something with factoring? So the bottom, I'm going to start by factoring out a 2. And the top, I'm also going to factor out a 2. That will leave me an x squared plus 9x minus 11, 22. Whoops. It's very possible that sometimes your teacher will make a little fancy mistake doing these problems. That's why they're so much fun. All right, so if I continue factoring, oh, well, first of all, these 2's I can get to cancel out, I think. That's one start. All right, so here we have limit as x goes to 2. We have x minus 2, and that's what we're going to try to factor because that's what we have in the bottom. So I'm just guessing that that might work with something like x plus 11 maybe? X is minus 2 plus 11. Ooh, that seems to work. All right, which then works out well when we are left with a limit as x goes to 2 of x plus 11. We plug in a 2 to that, and we get 13 is our answer. All right, so first we try to substitute. Second, we try to use our factoring opportunities. All right, these are in your book. I'm not going to go over all of these. There's an example 3 on page 62, and maybe we'll do a little example of all these properties in class too. And here is one other property that they mention in the book, but don't put with these properties. The limit of a constant is just equal to that constant. You know, there's nowhere to plug in an x in a constant, so your limit is just equal to the constant. All of these rules, sum, difference, product, constant multiple, quotient, and power rule, you should know all of them. Also, the polynomial and rational functions, if you have a function over a function, then it's the limit over the limit, provided that the denominator is not equal to 0. Okay, so there is a good example on page 62. Take a look at it. All right, now we also have trig functions. So we have some fancy stuff we can do with trig functions. First of all, if we graph sine of x over x, what we see is a graph like this. And I think it actually oscillates on the x-axis, goes up and oscillates all the way out, getting closer and closer to 0. On each side. But what we're really looking at as x approaches 0. All right, so here is x equals 0, which is the y-axis, that's x equals 0. And what number does this approach right here? If there's a 0, there's actually, I probably shouldn't draw a dot or a closed circle there. I should probably draw an open circle. But this heads toward the value 1. I'm going to give you formula sheets to work on, look at, and sine of x over x is equal to 1 as the limit as x goes to 0. This is something you should memorize, all right, and know. Correspondingly, sine of 2x over 2x is also equal to 1, and sine of 3x over 3x is also equal to 1. And those are just things you should memorize. There's actually something called L'Hopital's rule, which we don't really cover in calculus AB, but I think I'm going to show this to you in class so that you can also see how L'Hopital's rule gives us a 1. But graphically, for right now, if you look at these, that is what happens with the function at 0. It heads toward 1. Now, this fact we're going to use when we do other, I don't know if I have that one up there, but anyway, when we do other functions. Okay, so please note that algebraically, this is your, the 2x in this is your angle. You may not. It is against the algebra rules to cancel out 2's or to cancel out x's. This part on the top is protected by the angle authorities. Okay, inside that red, those red parentheses cannot be taken out, canceled, or checked off. It has to stay there. That is the sine angle. Do not try canceling out things. Okay, so what we're gonna do though is, since we know that 2x over 2x, 3x over 3x with the signs all are equal to 1 as the limit goes to 0, we're gonna use that fact to solve a lot of these problems. Okay, so the first one, we have limit as x goes to 0. Now that we know that sine of 4x over 4x would be equal to 1. And so what we want to do is take sine of 4x over x, but we want to make it equal to 4x on the bottom. All right, so if I multiply this by 4, then I also have to multiply the top by 4, right? To keep that an equal algebraic sentence. So this says that if I take the limit of this times the limit of this, I would actually use the product rule from the properties we just looked at, and this would equal the limit of sine of 4x over 4x is equal to 1 times the limit of a constant is 4, so therefore our total limit is equal to 1 times 4, or 4. Second example, we have sine of 7x over 4x, and we actually want this to be sine of 7x over 7x, so that we can equate that to 1. So I'm going to separate my 4 and my x in the denominator. All right, so those two are equivalent. Sine of 7x over 4x is the same as this over here, sine of x times 1/4. All right, so if we want to multiply the bottom by a 7, we're also going to have to multiply the top by a 7. And now we have something that we can take the limit of. We have the limit as x goes to 0 of each of these 3 items. We have 1 times 1/4 times 7, and that equals 7 over 4. And that will be the limit of sine of 7x over 4x. All right, so tangent's going to be just a little bit more fun, but not much. Remember from your trig identities, tangent equals sine over cosine. So we're going to write this, sine of x over cosine of x all over x. Now, remember what to do when you are, this could also be written x over 1. You flip the guy and multiply. So, algebraically, we have sine of x over x times cosine of x. Okay? And we want to take the limit of that as x goes to 0. So, limit as x goes to 0. Well, we already know what sine of x over x is, right? We know that sine of x over x, and then we're going to multiply that times 1 over cosine of x, and take the limit as x goes to 0. All right, so we have this times this. If we plug a 0 into here, we know that the limit is equal to 1. If we plug a 0 into cosine, cosine of 0 is 1. So we have 1 times 1. And so our total limit then is just 1. All right, so one more thing. So you have to do a little playing around with trig. And sine of x over x equals 1 when the limit goes to 0. Last but not least, we have non-existent limits. Some of them just don't exist because when you plug a 2 in, the denominator equals 0 in this. So you have 4 minus 6 over 0. It just does not exist. Sometimes I write this like this, DNE. And we're going to find out why it does not exist in day 2 of this lesson. And I wrote down the ones that don't exist, number 15 to 18. And we'll find out why tomorrow. Stay tuned. More excitement.